Alrighty, for exam one, essay number two, we are going to talk about resting membrane potential. We're going to talk about um, graded potentials and action potentials, and all the things that kind of make action potentials work so that we can have signals sent throughout our body and have a properly functioning body. So, to begin, we'll talk about what we call resting membrane potential. I'm going to abbreviate a few things just to save time. But to begin, resting membrane potential is when you have a cell, call this our cell, and the cell reaches a point of equilibrium. I guess not. It's more or less an equilibrium, but it's an equal point between ions flowing into the cell and ions flowing out of the cell. And primarily, what we're going to be focusing on today is potassium and sodium. So, we're going to start off by explaining kind of what resting membrane potential is, because there's a few different factors that affect resting membrane potential. The first factor that we'll talk about is what we call sodium potassium ATPase pumps. All right, sodium potassium ATPase pumps. And these pumps are going to move ions, sodium and potassium, against their concentration gradient. So there is normally a higher concentration of potassium on the inside of the cell and a higher concentration of sodium outside the cell. And then there's a little bit of sodium in here and a little bit of potassium out here. But what we're going to see is sodium is going to, or these sodium potassium ATPase pumps are going to pump out um, 3 sodium for every 2 potassium. Sorry about that. 2 A plus ions. And so the whole point of these sodium potassium ATPase pumps is to help the membrane reach its resting membrane potential. And essentially, all that means is potential just means having charge. So when we talk about potential, we're just talking about on either side of the membrane, we've got a little bit of positive and a little bit of negative on the outside. And so this this resting membrane potential is just a point that the cell reaches where it has a similar number of cations and anions on both the inside and the outside of the cell, and similar concentrations relative to their like the respective ions, like potassium and sodium. And um, like I mentioned previously, one of the biggest things that attributes to a cell achieving its resting membrane potential is the sodium and potassium ATPase pumps. The next thing that's really important is what we'll call these potassium leak channels. It's number two over here. These are going to be our these are going to be our potassium leak channels. Now, and something important to remember is these sodium and potassium ATPase pumps, number one, require energy, and number two, um, they need that extra energy in order to move the solutes across its membrane. But these leak channels, all these do is allow these potassiums, which are always attached to an anion, which is important to remember. These potassiums are able to just leak out of these little leak channels, and these leak channels allow potassium to move freely across the membrane, which helps achieve resting membrane potential. Um, the other thing to remember is that potassium is extremely permeable. And I will explain kind of why that's important to remember here in a moment because we're going to start talking about voltages. But we'll get that to the second. And then the third one is this is going to be our Na plus leak channels. And this allows sodium to move into the cell. Now, these are not very permeable. Sodium is significantly less permeable than potassium. So these leak channels aren't going to allow sodium to move, not allow a lot of sodium to move across the membrane. Um, and so let's see. Something else really important to remember about resting membrane potential is when we're talking about neurons specifically, I'm going to use a little bit of a bigger. So neurons specifically have a resting membrane potential of about -70 millivolts. And that's important because -70 millivolts um, is the resting membrane potential that allows action potentials to occur pretty easily through neurons. Now, every cell has a different resting membrane potential, slightly different. Like skeletal muscles, for example, are pretty similar actually to neurons. They're around -70. But if you have like a red blood cell, for example, red blood cells typically have they typically have resting membrane potentials of we'll call these red blood cells. They typically have resting membrane potentials of like I want to say it's like -30 or something. So fact check me if I'm wrong. Make a comment on the video when you guys watch this. Um, so I believe that's what it does, but that's important because there's not action potentials or signals being sent through the red blood cells, so that the concentrations of ions on the inside and the outside of red blood cells are going to be obviously a lot different than neurons. So that's why they will have um, different resting membrane potentials than neurons. Now, there's a few things that can change like the size or like the magnitude of the resting membrane potential. For example, if with potassium specifically, if potassium was left by itself, it naturally wants to reach a reach resting membrane potential at about -90 millivolts. So if sodium or excuse me, if potassium wasn't um, if you were going to have a cell with only potassium moving across the membrane, the natural resting membrane potential would be around -90. And the relationship between sodium and potassium obviously changes that. And we'll talk a little bit about like the Nernst equation and driving force here in a moment about as to why that is. Um, but sodium is always trying to basically bring the voltage of that cell closer to -90. Okay. Um, things affect the sign magnitude of resting membrane potential. Trying to make sure I didn't forget anything here because this is obviously pretty complicated, and I've tried to make sure I dialed in on studying this, but I feel like I'm missing one point here. Um, yeah, we can. Well, here I'll try to explain it like this. If we have a graph, let's say this is time in milliseconds, and this is our millivolts. So, and this is our neuron cell. we're going to have a point, we're going to have our resting membrane potential at negative 70 millivolts. And this is important because at negative 70 millivolts, this is where our cell naturally wants to rest at. So this is our RMP. And then we have all the way up here at about negative 55 millivolts. This is what we're going to call our threshold potential. And the threshold potential is important because threshold potential is what the resting potential of a neuron needs to arrive at in order for an action potential to proceed, or sorry, to propagate, I guess, to continue down. And so, um, yeah, what we're going to see is this cell constantly kind of like, slightly moving back and forth. Um, actually, that's a poor explanation of that. Trying to think of how to explain this a little bit better. Getting a little bit ahead of myself. Um, let's see. So yeah, we've got resting membrane potential there at negative 70 millivolts. We want to hit negative 55 in order for an action potential to proceed. However, I need to kind of explain. So let me rewind a little bit. Sorry, guys, this is a little bit confusing for whoever's watching this. I'm going to move this down. I'm going to talk about the Nernst equation real quick. Let's change this back. So the Nernst equation is an equation used to describe the movement of these ions across this membrane when we look over here at when we're trying to look at resting membrane potential. So the equation for the Nernst equation is E, which is basically the energy of the movement across the membrane, is equal to negative 61.5. And negative 61.5 is actually just a constant that you'd find like in a table or a book somewhere, divided by Z. And so um, Z is the charge, I believe, of the valence charge of the ion. So for example, like potassium and sodium, those would both be +1. But something like chloride, that would be like closer to +2. Um, so anyway, that's usually 1, and then you're gonna multiply that by the log base 10 of the concentration of ions inside the cell and ions outside the cell. And what that's going to get you is a value that will tell you the voltage at what the membrane rests. And so neurons, like we were saying earlier, is going to be closer to, um, for neurons, is going to be closer to like negative 70. Yeah, negative 70 millivolts. But for other cells, it can be different, like red blood cells, I said negative 30. And when you use this equation and you apply it to both, for example, if you just did potassium, for example, potassium would be negative 90 millivolts, like I was explaining earlier. Sorry, this is extremely confusing. I'm kind of jumping all over the place. Um, this is naturally where potassium wants to be at, calculating it with the Nernst equation. But when you include the calculation of sodium as well, that's where you kind of get this average of negative 70 that the cell wants to be at. So each individual ion has its own like Nernst equation potential that it wants to be at. And then the combination of all those ions is where you get, for example, like in a neuron, where you get that negative 70 value. Okay. Um, there's one last equation that we will use. that we're going to talk about real quick. We're going to talk about the driving force. Now, the driving force describes the net energy of movement that an ion would have when its concentration gradient essentially allows it to move across. So, like for example, when we talk about the propagation of action potentials, when sodium rushes into the cell, that energy that the sodium is moving across that cell membrane can be calculated with something we call driving force. And driving force has an equation, dF for driving force, obviously, is equal to Vm minus Ex. And so um, the membrane voltage is what the Vm stands for. And the Ex is what we're going to is going to be a value that we get from the Nernst equation. So essentially, you're going to subtract the value of the voltage of that specific ion minus um, the Nernst equation value that you'd get, and that would be the driving force that you would have for that specific ion. And so that's just important, just to be able to calculate those movement of ions, just to see, how much energy is actually moving with said ions. And if that's incorrect, again, correct me. I know I'm not perfect at teaching this stuff. Still trying to learn, but doing my best here. Um, let's erase this. Okay, now we're going to talk a little bit about graded versus action potentials. Graded. Graded versus action potentials. So a graded potential is a graded potential always precedes an action potential. Okay, so that's a pretty important thing to remember. So a graded potential is what we would see with the movement of ions across a membrane without using something like voltage gated sodium channel